So today's presentation will be talking about designing for efficiency in new plants or major plant renovations. Some of what we'll talk about today can apply specifically to major projects where you're looking at building a new facility on new ground, or a major renovation of your facility, looking at a new process, or moving equipment around the site. And some of these things will kind of apply universally across any kind of retrofit project at a facility. If you have questions during the presentation, there is a Q&A pane. If you enter your questions in that Q&A window, we'll make sure we don't miss them. We'll start addressing those questions at the end of the presentation. If you do throw a question in the chat, we may not miss it. Usually I have Cassie joining me on these and she keeps track of the chat, but with just me, I might not catch everything. So if you have a question, throw it in that Q&A pane. Again, feel free to keep saying hi to everyone in the chat. Everyone likes to say hi and check in with their friends in the industry. So getting into a little bit about who we are, the CDAC is an applied research program at the University of Illinois. We're based in Urbana-Champaign. We assist with buildings and communities in achieving energy efficiency, saving money, and becoming more sustainable. And our goal is just to reduce the energy footprint of Illinois and beyond. Our partners for the Public Water Infrastructure Program are the ISTC. They have a similar mission to us to encourage and assist citizens, businesses, and government to prevent pollution, conserve natural resources, and reduce waste to protect human health and the environment in Illinois and beyond. They also provide technical assistance, outreach training, and applied research similar to our program. Both of us have partnered with the Illinois EPA Energy Office to provide no-cost energy assessments for publicly owned and operated water and wastewater treatment facilities. As part of that program, we'll come out to your facility, document a bunch of information, and develop a comprehensive report for you, kind of listing cost of upgrades, giving you some estimated payback periods. We'll connect you with any applicable incentives and funding opportunities. That way you can help plan for future projects and improvements at your facility. We also provide continuing education events such as this one. So if you're interested in more, you want to see some of our past events, you can look at our website at www.smartenergy.illinois.edu/water. A little bit of what we're going to be covering today, kind of looking at some common sense designs that reduce energy consumption, identify some hidden efficiency designs that improve operating efficiency, review some examples of plants that have designed for efficiency and some that didn't necessarily do that, and how that impacted their operations. And we'll discuss some potential funding sources for resiliency projects. Joining me today is Amanda Stryker from Baxter & Woodman. She's the Assistant Wastewater Department Manager. As a Senior Project Engineer with 10 years of experience in a variety of wastewater and related projects, including pumping and lift stations, wastewater facility studies, plans and improvements, and HVAC engineering. She's the Costa Rica Department Manager and the Assistant Wastewater Department Manager. Her background in mechanical contracting provides real-life application to her designs. Amanda earned her Envision Sustainability Professional designation through the Institute for Sustainable Infrastructure, an infrastructure rating system developed to help designers, builders, and infrastructure owners build and direct infrastructure projects toward increasing levels of sustainability. And she is the CSWIA Illinois Section Trustee and the co-chair of the Biosolids Energy Efficiency and Resource Recovery Committee. So thank you for joining me today and helping with this presentation. A little bit more about our program. If you're interested in an energy assessment, you can apply at our website as listed there. To qualify for the Public Water Infrastructure Program, you have to be located in Illinois and be publicly owned. You have to agree to allow us to come out to your site and document information about your facility. You have to be willing to share that facility information with us, including operating reports if you're a water plant, and discharge monitoring reports if you're a wastewater plant. And the final assessment report is shared with the Illinois EPA Energy Office. It's a non-regulatory office, so you don't have to worry about any kind of regulatory backlash from sharing a report. I know that's a concern with some people, but it's just there to help document the effectiveness of our program. Once you apply for the program, we go through a data collection phase. We'll jump on the phone with you, gather some initial data about your facility so that we know what we're walking into during an assessment. And we'll gather 2 years of utility bills and your discharge monitoring reports. so that we can do some initial benchmarking for your facility. We'll bring that out to our site visit once it's scheduled, go over that information with you so you know where you stand relative to the other facilities that we've assessed in the state. And then we'll walk through your facility, take pictures of your equipment, talk to you and your operators about um, how the process is working. Are there any changes you want to see in your facility? And we'll use that to help develop that comprehensive report for you. So why complete an energy assessment? If you've got an existing system or you've never had a previous assessment, we can help identify missed opportunities, help you plan for capital improvements, uncover the potential possibilities for your facility. We can also lend that third-party support for your ideas for what your plant needs to improve. If you've got a new plant or it's been recently upgraded, there's always more that can be improved. We've gone to a lot of new facilities and found a lot of things that were engineered out and left on the table that have significant long-term impacts on energy consumption. We can help plan for future opportunities outside the scope of your most recent project. So again, looking towards the future for more sustainable operations. And there's always new technologies and processes in development. We can help bring those to light and inform you about what those technologies and processes might be. So a little bit about what I'm going to cover today briefly before I hand it off to Amanda to talk about her designs for efficiencies and stuff. We're going to talk about how to use wastewater data in the initial planning and design for a new facility. We'll talk about minimizing the fight against gravity as much as possible. Part of that will include minimizing recycle pumping where you can. Optimizing pump staging, making sure that that's operating as effectively as possible. Properly sizing your equipment, including aeration, your basins, the plant overall. Employing variable speed devices or timer systems to adjust for variable loading. Improving aeration control to optimize what's, for a lot of facilities, the largest energy consumer on the site. And decoupling mixing from aeration. As if you know, if you've got a basin with mixing dominated energy loads, that can throw off your aeration requirements, and vice versa. It ends up wasting energy. So first thing, looking at how to use wastewater data for sizing your new facility. Nutrient removal is coming for a lot of plants. And it requires a little bit more tuning and precision than just planning for BOD and ammonia removal. So knowing what's coming into your facility in that raw wastewater can help with sizing for your current needs, as well as planning for your future loading. So knowing that existing strength and flow coming into your plant can help better tune designs for what you need. One thing to note, with a lot of designs that follow 10-state standards or other design standards, they're planning for that future growth, and so they'll upsize your facility. A lot of times they have some conservative design standards in them that for most plants ends up oversizing equipment. And so while that's good for designing for future loads, you also need to take into account what's your current loading and make sure that your equipment can either stage down or has variable speed controls or some kind of modularity built in to handle what you have now so that you're not operating inefficiently now, planning for operating efficiently in the future as loads change or increase. Big thing that we've run across at a lot of facilities, particularly ones that have space restrictions, is fighting gravity. The picture on the top left here was a denitrification tower that was raised up about 20 feet, 25 feet to put some storage underneath that and just saves square footage on the site of the wastewater plant. But because they lifted that whole denitrification tower up, now they've got to pump that additional head. It's a continuous energy penalty that they'll be paying for the life of the use of that facility until some renovation down the road changes how that's constructed. Another one we've run across on the right side of the screen here was a recycle intensive process. The first couple of basins on the top of that image, if you're looking, I don't know if you can see my mouse indicator here. Top couple of basins had the raw influent coming in, and that was doing carbonaceous oxygen demand. So that was the initial treatment. Goes into some clarifiers. That was getting recycled back into the headworks and flowing back through that process. But then that was all getting pumped back uphill to run through an ammonia removal process stage. Um, and that then flowed down to some clarifiers where there was a secondary set of return activated sludge pumps for that side of the process. So there's 3 different sections here that are pumping water back uphill. That's a long-term energy penalty for this facility that maybe with some different changes in layout may have been able to be minimized. Next thing to kind of look into is optimizing your pump staging. We've been to a lot of facilities where the pumps have VFDs on them. And the way that they work is one VFD will ramp up until it's near full speed. Then the next one will kick on. They'll both kick down a little bit. And then they'll both ramp up again until they hit peak. And then a third one might come on depending on loads. But that's not always necessarily the most efficient way to stage pumping. What we're showing on screen here is if you've got a couple of pumps in parallel, if you're running one pump at a high flow rate or a moderate flow rate, you've got a higher velocity flowing through that pipe. So there's a little bit more friction head acting on that, which increases the pumping energy requirement. If you can split that flow through 2 pipes, you can reduce that pumping head and get some energy savings, particularly if you're applying a VFD to that system where you can adjust the speed of those pumps. So this information was borrowed from a previous presentation. Matt Johnson from Xylem provided this information to us. I want to thank him for providing this information. But this is just kind of an analysis that can be done on that type of system to figure out what the potential energy savings are from doing this kind of pump optimization staging. You can see versus running one pump at about 107 megawatt hours per year in energy consumption. If you're running 2 pumps, it almost cuts that in half. For this particular facility, it was netting about $6,000 in annual savings. Talking about system sizing and addressing current loads versus planning for your future loading and future growth in your communities. Building in a bit of modularity into your systems can have a big impact on how efficiently you operate now versus what your planned efficiency for the future is. So we were out at a facility down south that had a number of blowers in place. Usually they're only operating 2 of these under most of their design conditions. They might kick on a couple more under storm loading events. But the others are really there for future growth in the community and future loading coming into the plant. So they've got a lot of staging capacity here and modularity built into this system. The option on the right here was when we went out to up north, a couple of oxidation ditches out at the site. The majority of the time, they're only running the one oxidation ditch with a couple of mixer motors on it. The other oxidation ditch is used for storm flows. And again, as they have future growth, it may end up being needed more in the future. But they've got built-in modularity to their process here, where these were designed to handle both peak loads and normal flows in a more efficient manner than having a single large basin. Some consequences to oversizing your aeration basins. This was content that was given to us by Randy Chan at EDI. I want to thank him for his input on this presentation. The chop chart that we're looking at here shows a fixed DO set point operating at 2 milligrams per liter. But once the BOD in that basin is oxidized, the microbes are kind of starved then for resources. And so you start having endogenous respiration in that aeration basin where essentially it's acting like an aerobic digester. And so you've got a lot of tank capacity there that isn't being used for its intended purpose. You're wasting some aeration energy there. The bottom chart is showing variable output, process-based DO, where the DO set point is adjusted based on the loading coming into the basin. And so that full basin volume is ended up being used for the initial BOD oxidation without some of these negative impacts. So it improves your biomass health. You have less endogenous respiration within the basin, which improves some of your biomass settleability in the clarifiers. You're maximizing the performance of that process unit, both in aeration energy and use of the entire volume of the basin. You're increasing the process kinetics, so you're getting better processing capacity out of that basin. Again, you're reducing that aeration energy by reducing your process oxygen demand and improving the operating efficiency of that aeration equipment. Something else, looking at system sizing and adjusting for variable loads and stuff, is applying VFDs or timers or some other automation to your system to account for variable flows and loading coming into your facility. So the chart in the middle there is kind of showing a diurnal load profile where overnight you've got particularly low loading that the system needs to account for and back off. Both in producing aeration and flow rates through the plant. Otherwise, you end up wasting energy overnight, and that can impact your treatment quality. Timers are an excellent low-cost way to account for this. We see these lagoons particularly, where they can take advantage of kicking on aeration for less amount of time during the overnight hours, and during the day, those blowers are scheduled on more often. Prevents wasting energy by providing aeration to that lagoon more than what's needed by running those mixers and aerators 24/7. For basins that have DO controls in them, optimizing that DO control and set point can provide significant energy savings as well. So the chart here is just showing if you start with an initial DO set point of 3 is marked there on the chart with the square, and you reduce that DO set point to 2 milligrams per liter, that's somewhere around a 13% energy savings potential in your aeration equipment. If you can get down to a lower set point, about 0.5, we start seeing that for basins that are doing enhanced nutrient removal processes. Then you're looking at somewhere close to 25% energy savings potential for your aeration equipment. For a lot of systems now, as we're moving more and more towards enhanced nutrient removal processes, having better control of aeration in the basins is becoming more and more necessary. So don't have bleed over of DO from return activated sludge into anoxic or anaerobic zones of your process. And so we've seen in a lot of plants, some inefficiency just from manually trying to balance flows between different tanks as loading changes in the plant. And loading's never constant, so this is kind of a constant struggle to balance these systems and loading between tanks and aeration to different portions of the tank. We've also seen some struggle with balancing tapering your airflow, where at the inlet of the tank, you need a little bit more DO because that's where the process loading is highest. And then as the process is oxidizing microbes and nutrients in that wastewater, you need less and less aeration as you get towards the end of the basin. Trying to balance out zones with those can be difficult to do manually, especially with changing loads. So what's shown on screen here is an automated aeration valve, where each zone of the basin, each individual basin has a modulating automated valve that can balance the airflow requirements for that space. A lot more of our modern designs are including this automation as part of that process. So as we're looking at enhanced biological nutrient removal, sequence batch reactors, membrane bioreactors, moving bed bioreactors, and other simultaneous nitrification and denitrification processes. This automation is becoming more and more necessary to have tighter control over the DO, so we're not sending high oxygenated water back into processes that should be anaerobic or anoxic. To control those valves effectively and minimize maintenance on those valve actuators, one aeration methodology that seems fairly effective is most open valve control, where one valve is controlled to a most open point, and then you're adjusting your blower speed to maintain that valve nearly fully open, and other valves can then balance and adjust as needed to provide airflow for their particular zones. So what's shown on screen here, the top chart is the actual DO requirement in different zones of this tank. And the bottom chart is actually showing the valve positions. And you can see the top valve is being maintained at nearly 100% open. It's that most open valve control that has authority in this particular situation. Two of the other valves are kind of minimizing how much modulation they have, and only one valve is really having to adjust significantly to cope with loading that's coming into this particular basin. So again, this is reducing wear and tear on those automated actuators as each time they cycle introduces a little bit of wear. So a process like this can help minimize maintenance as well as improve energy efficiency for your facility. The chart on the left there is a histogram just showing for a particular process employing this type of control, how often they're within their DO set point and how close they are to that DO set point. So at the bottom of the chart, the error is very small. As you move up to the right side of that chart, the error is starting to increase. You can see most of the time they're within about 0.25 milligrams per liter at their DO target. A little bit more about optimizing aeration design. Again, looking at adjusting DO set points for changing diurnal loads. On the chart on the left side of the screen here is showing an example diurnal load. It has about a 5 times increase in the maximum loading versus that minimum loading at night. The table on the left there is indicating for different control strategies what the potential energy savings and impacts are. So the first chart is showing fixed blower operation with different DO set points of 1, 2, or half a milligram per liter. There's some potential energy savings there from the lower DO set points, but at those minimum load conditions, you're still over aerating and your DO set point's still going too high. So you can see the average DO set point at the average load for the day, instead of hitting your set point of 1 to 2 with a fixed aeration output, you're still over aerating to a DO set point of nearly 6 to somewhere around 5.2 milligrams per liter. And at that minimum condition, you're hitting nearly 8 milligrams per liter of DO. So the red text there is indicating if you can take that DO set point and adjust it based on the loading demand coming into the basin, you can get some significant energy savings and more closely match your DO set point throughout the entire diurnal cycle, which nets some significant energy savings on your blower system. So this would require having a VFD on the system, some kind of influent load detection, either ammonia-based sensors or some other technology that's detecting what's coming into your facility, so that you can adjust that DO set point as needed to match the load coming into that basin. And the last thing we touched on is decoupling mixing from aeration. In a lot of processes that have anoxic or anaerobic storage basins, those tend to be mixing dominated basins. And so if you're using aeration to also mix those basins, you're overshooting your DO set points. So looking at technologies, either the submerged mixer that's shown in the picture here, or large bubble mixers, or other mechanical systems, or intermittent aeration, things that can reduce that aeration energy when you just need mixing capacity for the basin, can reduce your energy consumption overall, and provide better DO management for those basins to improve your operating efficiency as well. And at this point, I'll hand it over to Amanda, and she can take it from here.
Excellent, thank you. Start my slideshow here. And now I lost the Zoom meeting. It told me I am not able to share my screen. Do you want to give me that option, or do you want to flip through the slides? Oh, and you muted yourself.
You should have the ability to share now.
Excellent, thank you. Screen too. All right, you got my screen?
Not yet. There we go.
There we go. All right. Thank you for the introduction earlier. Again, Amanda Stryker with Baxter and Woodman. I'm going to just go through today some of the parameters we look at when, as Sean mentioned, going through either a major overhaul, a new plant design, or just even simply selecting some replacement equipment at treatment plants. So we'll go through the proper planning to put in place, education of decision makers as a critical impact, preliminary design and reports, IEPA required versus actual design. Those are some of the points Sean just touched on as well. Looking at some of your large energy users, then owner and staff support and champion, and then we can have our discussion with the group. So proper planning is critical to identify what equipment is going to be impactful when looking at reducing energy consumption. Creating a facility plan report, especially if you're going for an IEPA loan, you have to have one of those, identifying some of the critical equipment that you plan on replacing. Doing a facility assessment, we often work with ComEd. I know Ameren has similar programs, but a very high level can be done for a ComEd or Ameren incentive program to identify some of your major energy users and how that would be impacted in the plan you have for your modifications at your treatment facility. Then going into a more detailed, comprehensive energy assessment. So looking at that detailed evaluation, you know, our blowers are using this much energy today. We plan on replacing them with, you know, new equipment and anticipate saving however many kilowatts per year by either operational changes, equipment changes, or control modifications. So getting into the detailed recommendations of specific equipment, specific runtime, and changes to your operation that can save certain energy throughout the year. Obviously, using CDAC as a resource and their reports as resources of what some of the big items are for energy improvements at your facility. It's always a great starting point to put you in the right direction for energy savings. And then in master plans and your facility plans, having a section on energy is always a key thing to consider. If it means, you know, a lot to you to save energy at your facility and what some of those major changes are going to be to do that and to reduce your overall electrical consumption. Having that in your plan as a part of your infrastructure and improvements projects moving forward helps you identify the bigger pictures in design considerations, and obviously meeting permit, probably most important, but then looking at reducing your energy consumption and helping save those O&M costs in the long run is critical as well. And then if you're able to, at your facility, looking at an energy neutrality plan. So if you're able to use CHPs through anaerobic digestion, put in solar panels, you know, there's a lot of really good programs out there now for incentives, and the energy pricing increasing is making it always more enticing to use your own energy that you can generate on your site, whether that be through anaerobic digestion biogas or solar panels. If your facility is in a point to being able to do some of those programs, definitely looking at the feasibility and the payback, and you know, how you can reduce and even maybe pay back to the grid. Education of decision makers. Wastewater treatment plants utilize a lot of energy in a community, and probably one of the bigger areas where a total city's energy goes is a wastewater treatment plant. And then within that, you have different areas within the treatment plant that utilize your most energy in specific processes. So aeration is your biggest consumption. Wastewater pumping and anaerobic digestion are your next large consumptions. And then just operating your building for lighting is rather large as well. So understanding where all of your energy goes in your treatment plant, and then making sure some of the decision makers understand that as well. So when you're proposing capital improvements and you may select a larger capital cost over, you know, maybe something that isn't quite as expensive but has a better energy efficiency rating, showing and proving to them that you can reduce some of your operation and maintenance costs with a little bit higher of a capital cost, and getting their buy-in and support through that is really important as well. So your advisors and the decision makers need to understand where all of the improvements are going to be impacting your treatment plan, and a lot of that can come down to energy. So once you have your plan in place and you're moving forward through your design, evaluating your equipment. I think that's something that we all do very, very early on in design phases, and looking at some of the critical things to evaluate: your capital cost, operating efficiency, energy usage, O&M requirements, polymer or chemical usage, operating range. We look at all of those compared against different manufacturers, different types of equipment, to really select which one is going to be the most cost effective. In that, it's very important to not just look at the capital cost or what some of the maintenance components are, but the total life cycle cost, the overall cost of ownership for major overhauls, operation and maintenance, and then considering energy increases each year and polymer increases each year, how those overall ownership costs are going to come out in the end. And that can lead you to selecting multiple or the best manufacturers. So we have a couple graphs on the right here that show the difference between the two costs for operating different types of blowers under standard conditions. Sean mentioned this a little bit too, designing for IEPA versus actual operation points. So the IEPA, everybody has their permit. You have to prove that you can meet your permitted conditions. A lot of facilities don't necessarily operate at their permit. So understanding that your equipment needs to be selected for permit operations, but also needs to be efficient at where you're going to be operating every day, because that's probably more critical in the grand scheme of operation maintenance of your facility. We have an example here. You have your IEPA loading, where you're actually loading at, where we have to meet certain BOD and PE removals for our equipment, and selecting what would be the IEPA loading and running most efficiently at our permitted loading may not be representative to where we're actually operating at today. So it might be more effective to have smaller equipment and multiple smaller equipment to operate more efficiently at your typical average point than two large pieces of equipment that'll hit that IEPA with the redundancy. So figuring out where you really want, or where you are operating most of the time, selecting that as your most efficient point, and then selecting the quantity of equipment, or maybe the right size of equipment that will get you to that IEPA permitted loading as well. So aeration was that largest energy user at a treatment plant. A lot of these examples come down to blowers. That's a big horsepower requirement. High efficiency turbos, very efficient in a tight range of airflow. Screw hybrids are also very efficient in a wider range of airflow. So two efficiency blowers, understanding which one is the best for your process, and then how to control the delivery. Your oxygen transfer efficiency is critical. So making sure your diffuser's selection has that oxygen transfer to reduce your air requirement, and then cleaning requirements, fouling can really impact your diffuser and your transfer. So making sure you're cleaning and maintaining your equipment to reduce and to maintain that energy consumption as a lower set point. Air control valves, iris valves are fairly new, and they provide a lot better control. So if you have a tight DO range that you're trying to hit, an iris valve versus a butterfly valves can certainly get the job done, but iris valves can have more precise delivery of air. So looking at the application, and if the which valve is more superior in that application. It's preferred to have each on each drop pipe, so you're getting the precise airflow to each section of the tank, and then actuated to meet the process demand from your probes, and then to control the output from your blower. More manual input can create, DO swings. When you have a higher loading coming in, you may not have enough DO because you're manually operating that valve and not adjusting in real time. Second large energy user is on your pumping system. So obviously we need to determine what we're pumping, liquid, sludge, or chemical, determine the pump best suited for that application, provide your VFD to match the process. And then in the instance of RAS from your clarifiers, if you can directly connect to each clarifier, that can help reduce the overall head by using the water level in the clarifiers. So just considerations on how to connect and pump and what you're actually pumping. Touched on this a little bit with the aeration, but allowing instrumentation and automation for probes, especially in your aeration tanks, your DO or ORP, having that set point and probe control your valves and your blower output can really reduce the manual aspect of operating aeration system, but also provide for real-time adjustment, and it's delivering exactly what you need to maintain your process treatment. We have here, it can create some risk for operators. A probe is only as good as it's maintained. So maintaining the probes and calibrating the probes to make sure that they're reading correctly so that we are providing the air that's necessary for the process treatment. Power monitoring on your MCCs and VFDs to identify how much power consumed is something we're seeing more often on some of our newer MCCs, tracking that power usage, and then SCADA for monitoring probes and energy usage. So tracking it in SCADA can help you find a trend, and when that trend starts becoming more out of sync or looks unusual to past trends, you can spot that pretty quickly and be on top of any issues that may be within your system. And that is what I had, and I don't have any other slides, but I'm able to answer some questions.
Thank you for that, Amanda. Appreciate it. Looking through the chat, don't see any questions have come in, but did see someone raise their hand here. So then it went back down. If you do have questions, please throw them in the Q&A. I did have a quick one myself. How can like a wastewater operator or municipality kind of start planning for energy efficiency projects and make that a focus? One of the things we kind of run across is becoming more energy efficient tends to be higher capital costs. So how they address that upfront cost versus the long-term impact when they're going to like a budgetary office or their municipality and asking for projects.
Yeah, so facility planning, I think, is the time to do that, and working with whomever may be writing your facility planning report and making sure they're aware that energy efficiency is something that is important to the wastewater treatment plant, and working in simple changes or modifications as you're going through that major overhaul. Something as simple as if we're changing the pumps out in the building gets all new lights as well. It does add to the capital cost, but as we saw, operating, just turning the lights on in a building can be 8% of your overall cost. So maybe modifying those to, LEDs or timer switches or whatever is preferred can save a little bit. So working in some of those maybe minor details into minor modifications, or when we're looking at some of the larger equipment overhauls, picking the best equipment and then proving and moving forward that full life cycle cost analysis to say, yes, it is more capital, but in the long run, we're saving more energy and it is more efficient and reduces the O&M on the electrical side.
Any comments on the use of artificial intelligence?
So predictive aeration, I guess, is maybe what I'm kind of thinking towards. I have not gotten there in any of my projects at this point. I think there's some facilities that can use predictive or AI to predict how their blowers are going to operate or how their pumps may need to operate, and we can plan for that, for those peaks. And I think I've heard a little bit on this, but I have not had much experience with AI on that. That's a very interesting and very timely topic, though.
We are seeing that as a growing trend in the industry, though, and we expect to see a lot more plants starting to employ artificial intelligence or digital twins. But a big component of those is having that influent sensor probes feeding information into those decision assistance tools, we'll call them, to give you accurate loading potential so that your system can properly adjust and have more efficient operation. Question came in, are MBRs more efficient than activated sludge?
They have an impact on footprint. Efficiency on activated sludge, I can't speak to that exactly.
I think a lot of it has to do with the process in your loading. I think anything can be designed to be efficient if you design it properly.
Correct.
We did get a string of questions about the iris valves, if you have any more information about those or experience with them in the field.
Yeah, we installed those at the Yorkville Bristol Sanitary District. I know we have received a lot of positive remarks on the iris valves. As far as manufacturers or how much they have saved to their energy process, I do not have that offhand, but I can follow up with a couple of those who have requested that.
And a question on the aeration optimization we talked about. Are there two separate set points for that DO control, one being pressure control for the blower and the other being the actual DO set point control for the actuating valves?
So how I would operate the system is select a DO set point for a particular zone. Your valve would open and close based on maintaining that DO. Your blowers would then ramp up and down to maintain a certain pressure set point and operate in their comfortable range as well.
And that's kind of how the most open valve logic works. The valves adjust to where they need to, with one valve that's in the most open position being kind of the control valve, minimizing how much the other valves actuate. And then as the pressure changes in the header of your air supply, that will adjust the blower speed. Not a question, but a comment. It is critical to have accurate influence sampling data when designing improvements. It will save a lot of headaches in the long run. Question here, how many of the process improvements from the energy audits have progressed forward into being implemented in Illinois? I have that data somewhere, but not right in front of me. I know we have done getting close to 200 total assessments for the state, with somewhere between 5 and 10 recommendations per report. We have implemented somewhere around $500,000 in potential savings from those projects. As far as the quantity, I don't remember that exact number. Are Scope 1 greenhouse gas emission reduction strategies being included during the design process of a new plant or major renovation?
Can you repeat that one? I don't see that one on my end.
Came in the Q&A, says, are Scope 1 greenhouse gas emissions reduction strategies being included during the design process of a new plant or major renovations?
So greenhouse gases, I know a lot of anaerobic digesters flare or are able to send that to a CHP to make use of that. There are still some gases, obviously, that come off of that system. It At this point, I'm not aware of any regulations on the wastewater treatment side that have to do with reducing greenhouse gas emissions.
It can be, though, if your local municipality has sustainability goals or anything like that, it can be included in that design process and consideration. Yeah.
Mhm.
Does most open valve prevent blower from running against closed valves when air demand is met? I would say yes. So once your demand is met and your valves, your most open valve is going to, the system is going to back off pressure so that one valve is nearly fully open at your demand point. So as your demand reduces, your air pressure is going to back off to make sure that particular control valve is at its nearly open position. Then other valves will adjust as needed to meet loading in their individual areas. And I believe that has covered all the questions that came in through the chat. I don't see any more in the Q&A. Oh, there was a question that came in early in the chat that I missed. Is this lead AP specific?
No.
No.
No, so that lead AP is mostly for, I would say, commercial buildings. The Envision ISI infrastructure rating is like lead for infrastructure. So it's similar. It's choosing not doing the project right, but also doing the right project. So making sure you're looking at the whole impact to the community, natural surroundings, climate and resilience, quality of life. There's a couple different categories there. So if the community or the municipality district is considering a lead type of certification to show their green initiative or their, you know, promoting or I'm trying to find the right word here, but their commitment to energy efficiency and green and forward thinking and sustainability, I would recommend the ISI Envision rating.
And I did mention at the start we would touch on funding sources. We have another Q&A while I'm pulling that screen share up. New plant design must account for future BNR requirements. DO may not be enough to achieve plant process optimization. Energy is not really a player in the game. I would disagree with that slightly. It is true. Future BNR requirements are a big driver of process improvements and things, but energy considerations are also a big component of that process consideration. You want to make sure your plant is going to be as efficient as possible when you get it set up.
So obviously, first and foremost, treatment plants have to meet their permit, right? We have to be considerate of the environment. We have to understand that our effluent is meeting the goals and we are not impacting water quality standards of the receiving stream. But as we do that, selecting the correct equipment and going through the process of looking at, operation and maintenance costs, energy efficiency, polymer consumption, chemical consumption, all of those kind of key critical points for equipment selection that we talked about, and then analyzing that life cycle cost. That's where energy really comes into play. No, you're still going to spend energy when you're treating wastewater, but how much, and how we can efficiently and effectively select that equipment to reduce that is a big driver.
So funding resources, CDAC's webpage, smartenergy.illinois.edu/water, has a link on it for funding opportunities. And on this page, we try to be a central location for everything that's available, from utility incentives and private grants to government grants and loan opportunities. So you can find all that information on our webpage. When we do our assessment reports, we always include the utility incentives, as they're a given fixed amount based on the potential energy savings. But we will also include in our reports links to other grant opportunities or private assistance. We don't usually include that analysis in our reports, though, because that money is a little bit more flexible. It's harder for us to determine you're going to get this amount in this grant. And so we do try to connect you with all that information, provide as much as we can to help you implement your projects and move forward with getting things on the ground. Amanda said, YBSD has the iris valves installed. I'm the liaison for the Yorkville City Council, and we'll get some more info from Cyrus. Okay. I think that's all the questions that we've had come in. If you have any other questions you think of after the presentation, feel free to reach out to me at spmaurer@illinois.edu, or we can
Sean, there
connect you with
was
Amanda.
one more when in the question and answer, and it was
Yep.
about the power cost being relatively low, 4 to 7% range. Energy efficiency does not fund capital investment. I would say that it's probably rare that the energy savings on replacing a blower is going to pay off for the blower. I think that's probably true, depending on what you're looking at for the capital investment. A lot of these energy efficiency items would come through from the facility plan and necessary improvements.
And a lot of the energy efficiency considerations too tie to non-energy benefits, such as improved maintenance, improved process quality, and things like that. So efficiency, as far as the energy alone, may not be the driver, but operating efficiency overall also includes energy efficiency and maintainability of the system. And so things like that also come into consideration and kind of interlink with energy efficiency as well. But yes, I agree. It may not be the driver for capital development, but it's an important consideration. Okay, well, thank you everyone for joining us today. Again, if you have any questions or follow-up, feel free to reach out to us. If you're interested in assessment or anything like that as well, we're happy to connect you with those resources. So thank you all for attending today. Have a wonderful afternoon.
Thank you.